3.1 Extreme Values. Hi everyone, today I'll be introducing extreme values and how they connect to calculus. What exactly are extreme values? Well, on a graph, they include maximums, and minimums. For example, on a graph, this would be the maximum, and this would be a minimum. There are two types of extrema, relative and absolute. Relative extrema are within a certain interval on a graph, and there can be multiple of them within that interval. In contrast, absolute extrema are the biggest and smallest values a graph can ever reach. For example, as you can see on this graph, this is a relative minimum, and there are multiple other extrema on this interval, such as maximums and minimums. This graph has an absolute maximum right here, because all of the other values on the graph go below this absolute maximum value. You can't go any higher. Now, let's go over the extreme value theorem. This states that if a function f is continuous over the closed interval from a to b, there must be at least one maximum and one minimum in that interval. Pretty simple, right? Let's move on to actually finding extreme values. Take a look at this graph. Note that at the maximum, the slope is 0. Therefore, we know that since the slope is 0 at this point, the derivative must also be 0. Let's try this out in an example. The first step to solving this problem is to take the derivative. In this case, we would use the power rule. Let's see. X cubed, bring the power down, subtract by 1, leaving us with 3x squared. 3x squared, bring the power down, reduce it by 1, giving us 6x. 3x, bring the power down, reduce it by 1, giving us just 3, and since negative 1 is a constant, it disappears. And now we have the derivative. The next step is to set the derivative, aka the slope, equal to 0. So let's write 0 equals 3x squared minus 6x plus 3. We can factor out a 3 from each of the terms, and we can be left with 3 times x minus 1 times x minus 1 again, giving us 0 equals 3 times x minus 1 squared, and giving us an x value of 1. The value that you get from setting the derivative equal to 0 is called a critical value, and that's what x equals 1 is. Always make sure to check if this isn't actually an extrema with a graph. Sometimes there can be a false alarm. Alright, this is what I got when I graphed this function on a graphing calculator, and here's what it looks like. You'll notice that there is in fact no maximum or minimum at x equals 1. But if there's no extrema, what's causing the derivative to equal 0 at this point? Well, if I zoom into the graph, it goes sort of flat at x equals 1, which is making the derivative equal to 0. It's a false alarm though. We call this sort of point a plateau. Note that critical values aren't necessarily extrema. They can also be plateaus, so that's why checking your answer is always important. Now, this problem isn't over yet. Remember that the bounds on this problem are inclusive, so we have to consider the endpoints as well. In this case, the endpoints are -1 and 3. We'll have to test -1 and 3 to determine which kind of extrema they are. We find that f of -1 equals -8 and that f of 3 equals 8. This tells us that f of -1 is a relative minimum and that f of 3 is a relative maximum. Now, there's a special case when it comes to finding extrema. An extreme value doesn't always happen when the derivative is 0. For example, take this absolute value graph. We can clearly see that there's a minimum at x equals 0, but what's the slope at that point? Looking at the graph, we can't determine the slope because it's such a sharp turn. These sharp turns are called cusps. Since it's not possible to determine the slope at a cusp, the derivative does not exist at that point. Therefore, we now know that there are two cases in which there can be a critical value, when f prime is equal to 0, or when f prime does not exist at a cusp. Keep this in mind when finding extrema. Now in this example, we have to find the absolute extrema of f of x on the closed interval -5, 4. So let's take the derivative. In this case, the derivative is 3x squared plus 6x minus 9, and the -18 is a constant, so it disappears. Now let's take the derivative and set it equal to 0. We can extract the 3 to give us 3 times x squared plus 2x minus 3, which can then factor into 0 equals 3 times x plus 3 times x minus 1. And this gives us x values of 1 and -3. But we must also remember to include the endpoints, which in this case are -5 and 4. Finding absolute extrema involves testing each one of the x values we obtained previously. F of 1 equals -23, f of -3 equals 9, f of -5 equals -23, and f of 4 equals 58. This tells us that x equals 4 is an absolute maximum, and that both f of 1 and f of -5 are absolute minimums. And there we have our answer. We found the absolute extrema of the function on the closed interval. Let's try a harder example involving trig. In this case, we have to first take the derivative. F prime of x equals, well, the derivative of sine x is cosine x. So we can say 2 cosine x minus the derivative of cosine x is negative sine x. And then we have to use the chain rule, so multiplying it by 2. And so we can set it equal to 0 and say that 0 equals 2 cosine x plus 2 sine 2x. We can cancel out the 2's because they're just constants, and we can move the negative cosine x over to give us negative cosine x equals sine of 2x. And then when I plug that into a calculator, I get that x is equal to pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. Now, using a calculator, I can see that at x equals pi over 2, there is a maximum. At x equals 7 pi over 6, there is a minimum. At x equals 3 pi over 2, there is another maximum. And at x equals 11 pi over 6, there is another minimum. And that is our answer.